the Thimne copy. Now we are recording, exactly. Today we have with us a very good PhD candidate at Thimne, for Thimne UPC, Ivan Rivet, currently supervised by Professors Narges de Alami, Miguel Cervera, and Michele Chiumenti. And he's going to speak a little bit about mechanism-based damage and multi-scale failure of fused filament fabrication components for additive manufacturing, right?
Yeah.
Thank you very much, Ivan.
Okay, thank you, Alejandro, for this nice introduction. As he said, I'm a PhD candidate under Miguel Cervera and Narges de Alami. And in today's presentation, I will present some of the recent advancements in my PhD thesis called Mechanism-Based Damage and Failure and Multi-Scale Failure of Fused Filament Fabrication Components. The presentation will be structured in the following way: motivation, methodology, results, and conclusions. And I have divided the methodology and the results into two separate parts that I call elasticity and failure and damage and fracture. I will explain later why this subdivision is made. So before entering into many details, I will talk and define what is additive manufacturing. So additive manufacturing, based on the ISO and ASTM standards, is the process of joining materials to make parts from 3D model data, usually layer upon layer. Among these, let's say, additive manufacturing technologies, several strategies exist and several classifications can be made based on different criteria. For instance, we can see that there's material jetting technologies, direct energy deposition, and material extrusion. All of them are additive manufacturing strategies. The ones we are focusing on are the polymeric-based additive manufacturing technologies, those technologies that use polymers as the raw material, and more specifically, the fused filament fabrication technology, which is the most well-established one. This fused filament fabrication technology is based on using a polymer as the raw material that is heated until its glassy temperature, and then extruded through a nozzle and deposited into a building platform. This building platform deposition follows a specific path, and this process is repeated layer by layer until the whole component is built. We can see that this polymeric-based additive manufacturing technologies has a lot of different available common materials such as ABS, PC, PLA, and so on. So why are we studying fused filament fabrication technology? Well, it has a lot of advantages, such as its design freedom that it allows, because you can conform almost any kind of geometry. Also, its cost effectiveness, which makes it extremely useful for rapid prototyping, and also the wide range of polymeric materials that are available in the market, as I've seen in the previous slide. The components that are used in this technology show a very reduced weight because, as we will see later, the inner zone of these fused filament fabrication components is conformed mainly by air gaps in order to reduce material waste and also reduce the manufacturing time. And because we are reducing material waste, there's a very small footprint during the fabrication of these components. However, even though there are some advantages, there are also some disadvantages, such as the relatively long processing time that takes to manufacture these components, and also the complex material properties that these components show due to the layer-by-layer manufacturing strategy, which makes that the process planning, meaning the selection of the optimal parameters for the manufacturing of these components, is crucial. And this is the main focus of this work. In this slide, you can see all the different available, or some of the different available process parameters in these technologies. And among all of them, we are focusing mainly on the printing direction, because it's the, let's say, the process parameter that the user has the most influence on and the most, let's say, control on, and one of the parameters that has the most influence on the final mechanical properties of the component. So both methodology and results, which are the main sections of this presentation, have been divided into two parts. And the reason behind this division is what I'm trying to show you here. Basically, in a very standard force displacement course, we can roughly divide it into three different sections. The first section, where the material presents a linear behavior, a linear elastic behavior, that we call, let's say, the elastic part. Then we have, oops, did I touch anything? Okay. We have the damage part, let's say the stiffness degradation part, or the zone where this linear elastic proportion does not hold anymore. We can see some non-linearities arising. And then we have the fracture part in which the component loses all stress, let's say, current capacities, and it breaks. This first part over here is the one that has the most commercial interest, because in the end the clients only want to know, let's say, if the component breaks or not, and how is it behaving during its expected behavior, let's say. And this second part has more of a research interest and also some indirect commercial interest, because in the end, the more you characterize the material here in this damage or fracture part, the more you know in general. So regarding the elasticity and failure, in order to characterize this model, this material, we establish a modelization of its material, of its constitutive behavior. It is generally known that additive manufacturing components, since they are built layer by layer, they show orthotropic material, orthotropic constitutive behavior. However, we go one step further and we modelize every single printing pattern that is available or that is present in a fused filament fabrication component as an orthotropic material by itself. We distinguish mainly 3 different printing patterns in fused filament fabrication components. The first one is the aligned filaments that we call the contour zone, which is the zone that is around the component, let's say that conforms the lateral walls of the component. Then we have a second printing pattern called the crossed filaments, which is the cover zone, meaning the top and bottom covers of the component. And then we have a third printing pattern, which is the inner zone, that in the end can, let's say, be conformed by many different printing patterns and many different infill densities. So the first two, the contour and cover zones, are characterized via tensile tests. Since each of these printing patterns behaves orthotropically, we are characterizing each material direction independently. And then for the last part, the inner part, since there are several printing patterns that can exist, such as zigzag, grid, triangles, and within every single printing pattern we can see different as well infill densities, it is extremely expensive and useless to characterize via experimental tests this printing pattern. Therefore, the approach that we are following, we are performing, let's say, computational tests, a computational characterization. In order to perform this computational characterization, we make use of a multi-scale analysis. What is a multi-scale analysis? A multi-scale analysis is any analysis in which there is a scale separation, meaning we are analyzing 2 or more different scales at the same time. In this example, our case, we are modelizing the macro scale as a uniform, solid, continuous, and homogeneous medium, and then we are defining our micro scale in which we are defining all the geometrical complexities in these components, such as the interaction between adjacent filaments, the interaction between adjacent layers, and so on. There's several different ways of performing a multi-scale analysis. One is called the finite element square method, which is based on brute force analysis, meaning we are solving both scales at the same time. This is extremely computationally expensive. There are several ways of, let's say, reducing these expenses, such as using reduced order models, using machine learning, but still it's very expensive. The approach we are following is we are performing what is called a computational homogenization. In this computational homogenization, we are performing, let's say, calculating the constitutive behavior of the micro scale as it was, let's say, a whole homogeneous solid medium. How is behaving this medium, which is the constitutive tensor of this medium, so that it behaves as if it had all the geometrical complexities in it. Let's say, general scheme, the way in which the steps to perform this computational homogenization is we first apply a macro strain field in this component, or in this geometry. We perform, let's say, this macro strain is scaled, or let's say is applied in the form of micro displacements. This micro displacements is solved as a standard boundary value problem. We obtain some micro stresses, and then we perform an upscaling or a homogenization of these micro stresses, obtaining the macro stresses. This homogenization is basically a volume average. And then the ratio between these two macro strains and macro stresses is what we call the macro constitutive tensor, that then later on we use to solve the macro scale. So once we have, let's say, characterized our model, our material, we have to start producing our, let's say, our mesh domain. For standard methods, the meshing of the component starts, or the parts, from a CAD model, and more specifically in 3D printing, the first step in producing these components starts the parts from an STL file. An STL file is basically a surface-based file type, which is not the best option for performing a mesh, because in the end it has, let's say, a lot of errors. It implies a lot of, you require to do a lot of repairment processes, and it's not the optimal way of let's say, generating our mesh. However, this STL is required because in the end, in a fused filament fabrication, let's say, process, this STL file is sliced at several heights, and the intersection between a horizontal plane and this STL file conforms a path, and this path is the one that is used in order to fabricate the component. Okay? The translation from this process, let's say from this STL to this code that is called G code, is called a slicing process. And since this G code still contains all the geometrical information that we require for the component, is the one that we are going to use to generate our mesh. How are we performing this generation? So this G code is nothing more than just lines defined by 2 points. Therefore, what we do is we define a bounding box, meaning a box that contains with the maximum minimum dimensions of our component. We divide this box into several elements that we call voxels, and we perform an intersection of every single path that is present here into the boxes that we have. All the boxes that are intersected form part of the geometry, and the boxes that are not intersected are disregarded, basically. And this will be the final result of a voxel. However, there's a problem with this strategy, and that is that in order to capture all the geometrical complexities of this component, we have to define a very, very small element, which implies a lot of elements and therefore a very expensive simulation. And in order to solve this problem, we perform an adaptive mesh refinement, meaning that we coarsen the elements that are far from this geometrical, let's say the parts of the geometry that are more complex. We coarsen the elements, and therefore we reduce the total number of boxes that we analyze. Let's say in a very schematic way, how is this made? For instance, in this first element in 2D that we have here, let's say that we want to perform an intersection of this bounding box with this hatch. Since this hatch is intersecting the only element that we have, we perform a subdivision of that. In the next step, we'll again perform a division of all the elements that are intersected with this path. In this case, it's only this top left element. We repeat the same process, intersecting all the elements that are, refining all the elements that are intersected with this path until the desired accuracy is reached. Therefore, we can see that we have very small element size in here and very large element far from the geometry, reducing a lot of the computational expenses. In this video, I will try to reproduce. We can see live how is this mesh generated. Since again, fused filament fabrication components are built layer by layer, we can see how is this component virtually built, let's say, and we can see that the elements have a much finer element size in the top layers, and once this top layer is getting far and far away, the elements are being coarsened. Once the mesh has been generated and the material has been characterized, we enter in the second part of the methodology, which is called damage and fracture. In order to establish and modelize when is the component damaging, or when is this, let's say, establish a threshold in which we go from the linear regime to the non-linear regime, we have to explicit a damage criterion. Several damage criterion exist, such as the typical von Mises criterion, and so on. But for, let's say, plastic materials that have orthotropic properties and that have different strengths of tension and compression, the typically used damage criterion is the Tsai-Wu criterion. This Tsai-Wu criterion computes a stress factor F that is computed using a linear and a quadratic term, and this stress factor is normalized, and therefore it has to be less or equal to 1. If it's higher than 1, it means that the material is damaging. It is going into the nonlinear regime. The matrix, well, the array Q and the matrix P are basically based on the material strengths of the material, which are characterized in this way. However, the previous, let me go back 1 second. The previous, this Tsai-Wu damage criterion has one drawback, and that is it's a single smooth function, meaning it is just one scalar, and just one scalar is impossible that you fully characterize all the different failure modes that are present in such a complex system. Because in the end, let's say the different printing patterns that are present in a FFF component have more than one failure mode, and one single parameter cannot capture all the physical singularities that appear there. Therefore, what we have done is we have developed a mechanism-based damage criterion. In this criterion, what we are doing is we're expressing one stress factor different in each direction. For instance, we have these aligned filaments that are aligned in the x direction. Therefore, the failure is different in the x direction than in the y and z directions. For the x direction, if the ratio of the normal stresses in the x direction with the strength in the x direction is higher than 1, we indicate that this material is failing. However, this is only for the case where the stresses are positive, meaning that the filaments are under traction. If the filaments are under compression, a buckling occurs. More specifically, a phenomenon called fiber kinking occurs that is slightly more complex than a buckling, but in the end is driven by that phenomenon. And therefore, we use another different formula. And for the y and z direction, since it is a brittle type of fracture, this failure mode would be due to the decohesion between both either adjacent layers or adjacent filaments. We use a more Coulomb failure criterion that is normally used for brittle materials. And the same process applies for the crossed filaments. In this case, in these crossed filaments that are stacked in the XY plane, the Z direction is the one where the cohesion occurs. Therefore, there's a brittle failure, and therefore we, in the Z direction, use the more Coulomb criterion. For the X and Y direction, since it is an isotropic plane, we use a von Mises criterion. Once we have established a threshold in which the material goes from the linear to the nonlinear regime, we have to specify a damage evolution law. How is this damage affecting the stiffness? For the Tsai-Wu criterion, since we have only one parameter, we map this parameter using an isotropic damage model, meaning that we are mapping our stress factor into a damage variable D that goes from 0 to 1, meaning 0 that the material is not damaged and 1 that the material is fully broken. And this isotropic damage model considers that the damage parameter affects equally all the components in the constitutive tensor. However, since for the mechanism-based criterion we have one stress factor different for each component, we use an orthotropic damage model. In the orthotropic damage model, we have, instead of one damage parameter, we have 3 damage parameters in the X, Y, and Z direction, and these parameters affect differently each direction of the component. The stiffness differently in each direction of the component. This damage evolution law follows the Tucker consistency conditions, and it is a perfect damage law, meaning that not hardening nor softening is considered. And finally, once we have established the stiffness degradation, we have to model the breaking, the fracture of the material. In order to model this, we have established a new mechanism. We have developed a mechanism-based cracking model. In this cracking model, basically, we establish that if the square root of the tau value that we have computed, or the square root of the stress factor that we have computed, is higher than a certain value that we call alpha star, we set our damage equal to 1, meaning that we fully break the material. The main question here is how are we computing this alpha star? Well, we are defining an alpha rate of 9 components. Each component is used for each material direction, and we are distinguishing tension and compression, meaning we have one alpha parameter for X traction, one for the X compression, and the same goes for every single direction. And then we have 3 different alpha parameters for the shear. Then we are computing an array beta, where this array beta has again 9 parameters, analogous to the alpha array. And this array, in each parameter, we are calculating the ratio between its corresponding stress value with its corresponding strength value. Again, we are distinguishing tension and compression, and we have the 3 shears here at the end. And in this beta rate, the component that is the highest one, the maximum component, meaning the direction or the failure mode that is under the highest solicitation, we are selecting that alpha value over here. These alpha array are basically material parameters, and those alpha that correspond to the cohesion, let's say to weaker strengths that we already know. For example, in the case of the aligned filaments, the Z and the Y directions are weaker direction, are brittle fracture. Those parameters will be much lower than the rest of the parameters. So, showing some of the results that we obtained so far regarding the computational homogenization analysis, we saw that, well, we solved, let's say for this, I'm showing this example for the plus minus 45 printing pattern. And in this example, we solved and calculated the different material properties, let's say the Young's modulus in the X direction, Young's modulus in the Z direction, and so on. And we calculated for different infill densities, going from 10 to 70 infill density, for 3 different materials: PLA, ABS general purpose, and ABS polycarbonate. And what we saw is that these properties are independent of the used material, and they only depend on the infill density. Therefore, this computational homogenization not only saves us a lot of experiments, but also it shows us that these strengths do not depend on the used material. Not the strengths, the material, let's say, elastic parameters. We repeated this same analysis not only for the let's say not only for the infill, for the inner zone, but also for the aligned and cross filaments. And we saw that this analysis can be performed as well via computational homogenization, because in here we are comparing in blue the computational results with, in red or green, the experimental results. And we can see that for all material properties, the relative difference is very low. Therefore, we can not only compute via computational homogenization the inner properties, but also the properties for the cover and the contour. These are the results in the previous slide. These are the results for the aligned filaments, meaning the contour zone. And these are the results, the analogous results from the cover zone. This model was again calibrated and validated via several experiments. First of all, it was calibrated and validated in the linear regime. You can see, basically, that the simulated force displacement lobe always falls within the experimental range in both cases, in both experiments. And once this model was calibrated and validated, we performed the analysis for the non-linear regime. For the non-linear regime, we basically did 2 experiments. The first one is this standard and classical 3-point bending test, in which we are analyzing 3 different printing orientations. The first one is horizontally printed, and the load is applied in the top face. The second one is horizontally printed, and the load is applied at the lateral face. And the last one was vertically printed. And we performed the we compared the experimental results with the computational results using the Tsai-Wu damage criterion with the computational results using the mechanism-based damage criterion. These are the contour fields of the damage variable, and we can see that in this simple case where only normal stresses appear, there's only one failure mechanism possible that appears always in the middle. And of course, this phenomena is properly captured with both Tsai-Wu and mechanism-based criterion. If we take a look at the force displacement curves, again, we can see that the difference between the experimental results and the computational results are low for both Tsai-Wu and mechanism-based damage criterion, except for these 2 cases over here. And the reason behind this phenomena is the failure mechanism that is occurring. For instance, in the vertically printed specimens, which corresponds to the 3rd row, we can see that the failure occurs always at the bottom face, and in this example, the bottom face, let's say the filaments are printed in this direction, and the failure occurs due to the decohesion between adjacent filaments. In the H90 case, if we perform the same analysis, the failure occurs due to the breaking of the filaments. While in the first case, the failure occurs due to a plus minus 45 breaking of the filaments, which is a much more complex failure mechanism that is slightly more difficult to capture with this modelization. And the second experiment that we did, which is the most interesting one, is a door handle test. In a door handle test, not only normal stresses appear, but also shear. There's a combination of a bending and a torsion moment, and therefore more complex stresses arise. If we take a look at the experimental results, we have printed 3 different orientations, orientation 1, 2, and 3, and we have analyzed 2 different infill densities, 25% infill density and 50% infill density. And what we can see is that the failure not only depends on the orientation, but also on the infill density that was used. For example, for the first orientation, we can see that the failure occurs at the corner and, let's say, horizontally, meaning it follows the direction of the layers. However, this happens only when it is printed with 25 infill percent. When it is printed with a 50% infill density, we can see that the failure occurs at the base, even though it was printed using the same exact orientation. If we go to the second orientation, the failure occurs diagonally for both infill densities. And if we go to the third orientation, the failure occurs vertically. These are the experimental results. Let's now compare the results with the computational results. If we use the Tsai-Wu damage criterion, we can see that the failure is always detected at the corner, meaning it fails to modelize this special case over here where it fails at the base. Not only that, but also in these special cases where the failure occurs vertically, this is not properly captured because it detects, let's say, it predicts that the failure occurs diagonally even in these cases. However, if we use, instead of the Tsai-Wu, we use the developed mechanism-based damage criterion, we can see that the failure, this special case over here, where the failure occurs at the base, is properly captured with this criteria. Not only that, but also in this orientation 3 results, where the failure is vertical, let's say following the layer's direction, it is again properly captured in these 2 examples, using the mechanism-based damage criterion. And of course, the orientation 2 results show the same results as in the Tsai-Wu, which means they break diagonally as the experiments do. If we now take a look at the damage criterion, these conclusions get, let's say, we get the same conclusions, meaning that for the first orientation, orientation 1, we can see that the blue line corresponding to the mechanism-based damage criterion falls a lot better the experimental results than the red line corresponding to the Tsai-Wu criterion. While for the orientation 2 and orientation 3, similar results are achieved with both criteria. Therefore, the main conclusion that we can draw is that, first of all, the 3 material model, meaning the printing pattern-based material model, is a proper characterization of these components, FFF components. Then also the computational homogenization is possible to be done with not only the inner but also the aligned and cross filaments. And finally, regarding the 2 damage criteria that were used, the Tsai-Wu criterion is a good indicator, and it's normal that it's being, let's say, used in a standard way in the industry, but it's only a good indicator for simple stress states. When you use it for more complex stress states, where shear, normal stresses, and more different, let's say, special combinations appear, it is not a good indicator and fails into, let's say, capturing the failure mode. While the mechanism-based damage criterion, it takes this, it correctly predicts the breaking mode and is, let's say, it's more appropriate for complex stress states. Well, these are some projects in which this work was done. And these are some papers that have been published. There's a final paper in which we are trying to publish. It is almost published, but well, hopefully in the next month it will be done. And that's the presentation. Thank you very much.
Thank you, Ivan, for this impressive presentation, which I will ask you the PDF later. Thank you.
Of course.
If there are any questions from the audience, maybe in here, or I mean, I have many, but I will do them private. I think otherwise. But let's wait, or maybe in the meantime, I have one question. Can you go to that slide in which you are trying to characterize the orthotropic one directional material. You know, if you
The aligned, you mean for the damage criteria?
I mean, you have this kind. You have this two, right? And you're trying to characterize independently both of them.
Exactly.
Wouldn't be possible to characterize this one, which seems to be easier, and then by rotating and applying compatibility, predict the properties of the other one?
The thing is, in the end, if you take a look at the
Like in a stacking, you know, I mean,
Yeah,
in
I
the end, it's the same material but rotated and with some compatibility.
I know, because you are right, because in the end, if you take a look at the what we call the representative volume element, this is for the aligned filaments, and if you take a look at this and this, in the end, is the same one but rotated 90 degrees, extra 90 degrees. It's a good question, because in the end I have seen some softwares like Alter, where they perform similar characterization. They use this as the basis, and then they build the second one using the geometry. However, they only recycle, let's say, the geometry, not the mechanical properties. Therefore, I don't know if that would be. For sure, it is possible. I don't know how difficult it is, though. But yeah, it should be possible.
Well, with this one, it shouldn't work that easily, because it's not only rotated, but it's also, well.
Yeah, but the thing is, the geometry has to be here periodic in order to apply the conditions. But it should be possible as well. You should get the same exact results if you put this half stack.
Yeah, that's true. That's true. Any questions? Well, I have only another curiosity. When you're building the additive manufacturing sample in the simulation that we saw that very fancy video,
Yes.
that mesh was there before, or you're creating the new elements on the run?
Yeah, the thing is, you start with one element, one whole element, which is the bounding box we call, and you start with one path. You refine all the elements that are intersected by that path. Let's say we start with one. Obviously, that one is intersected. You subdivide in 8. You keep refining until you reach a certain level of accuracy that you define, and then you go to this next path.
So you have this super coarse ghost mesh that you are refining as needed.
Yes. And then there's also like a coarsening of once you have intersected everything, you can perform a coarsening of the already intersected.
How much it costs this procedure, this mesh procedure?
It depends, of course, it basically depends on the refinement level that you define. But for instance, I have actually, let me take a look. Yes, here. Here I made some sensitivity analysis of using the coarsening and not using the coarsening. And the thing is, for the mesh generation, if you don't do the coarsening, it takes very few time. If you do it, it takes a lot more. But the thing is, the reason behind this coarsening is in order to get much faster simulations. Yeah. And in the end, this, let's say this, even though the mesh generation time increases, the simulation time decreases more than so you gain more than this.
Possible to use some other strategy. You are restricted to use hexahedral meshes. So
well, in the end, they are in general more accurate than tetrahedra, so we just stick with it. Yeah, we haven't considered. In the end, since we are also using the homogenization, which is a hexahedron, it fits perfectly in that strategy. We haven't considered it, but it would be possible.
Isogeometric, no.
No, we haven't.
The next PhD candidate.
Maybe.
Thank you for the questions. At home, there are no questions. Well, virtually, let's say. So, well, let's close the session then. Yeah. Thank you very much for the attendance. Thank you, Ivan, for this very nice presentation. Interesting. And well, good luck with the next steps.
Thank you.
Thank you for.
Thank you, everyone, for coming. Yeah.
Thank you. Do not forget the pen drive.
Yes. Me he olvidado, de hecho.